In this video, we're going to continue to look at some details of bonding in organic molecules. In our last video, we saw that if carbon is attached to 4 groups, it could be sp3 hybridized. What if instead carbon is attached to 3 groups? So for example, we could be looking at something like ethylene, where we have a carbon-carbon double bond, and each carbon is connected to 1, 2, 3 groups. Let's think about the electron configuration of carbon: 1s2, 2s2, 2px1, and 2py1. And we'll just focus on the valence electrons, and we can fill in the electron configuration. These are our 2s orbitals, a 2p, and another 2p. In this case, before we think about hybridization, we can think about it as if we are exciting one of these electrons, so that we're looking at an excited state where we have 1 electron here and then 1, 2, 3 electrons in the p orbital. And now we can think about the hybridization, but rather than blending the s orbital and the 3p orbitals, this time we'll blend the s and only 2 of the p orbitals. So the s and 2 of the p orbitals are going to be blended to give 3 new orbitals. These orbitals are called sp2 hybridized because they are made up of the hybridization or the blending of 2 p's and 1 s. 2 p's, 1 s. In addition to these 3 hybridized orbitals, we also have a p orbital left unchanged. So that is still up here. Let's put our electrons back in, and now we have 1, 2, 3 electrons in the sp2 orbitals and 1 electron in the p orbital. And now we can see that we have these 3 half-filled sp2 orbitals, which can make 3 sigma bonds, and we have an unchanged p orbital, which could be involved in the formation of a pi bond. And so we can use these to explain the bonding in ethylene. Once again, as we apply valence bond theory, including hybridization, let's now focus on sp2 hybridized orbitals. In terms of energy, the sp2 hybridized orbitals will have the same energy as each other, and the relative energy will be in between an s and a p orbital. In terms of the shape and geometry, the shape is going to look something like this with a little nub. And once again, we're going to ignore that little nub so that it looks something like this. And when we put them together, our 3 sp2 orbitals are all in the same plane, and there's angles of about 120 degrees. So when we're talking about a carbon with sp2 hybridization, we can think of it like this, where our sp2 orbitals are in the plane, but then we also have to remember that there is a p orbital. Rather than having this in the plane of the screen, I'm going to redraw this perpendicular to the screen. So we'll have this one in the plane, and then here is an sp2 orbital back behind the plane, and then this one is in front of the plane, because then that leaves us able to show our unchanged p orbital. So these are our 3 sp2 hybridized orbitals, and this is our unchanged p orbital. Furthermore, if you remember the electron configuration, we had each of these orbitals was half-filled, including the p orbital. So now with our half-filled orbitals, we can think about orbital overlap using valence bond theory. So as we consider the bonding in ethene, which is also called ethylene, let's say this is our first carbon, and this is an sp2 hybridized orbital. This is an sp2 that's going back behind the screen, and this is an sp2 orbital that's coming in front of the screen. And this is the p orbital. Now keep in mind, all of these orbitals are half-filled. And now let's look at our second carbon, which is also sp2 hybridized. So here's an sp2 orbital. Here is an sp2 orbital going behind the screen. Here is an sp2 orbital coming in front of the screen. And here is a p orbital. And remember that these are also half filled. So now that leaves us with hydrogen, and we have a hydrogen s orbital that can overlap with this sp2, another hydrogen, and another hydrogen. So this sp2 orbital is overlapped with this sp2 orbital to form a sigma bond between the two carbon atoms. This sp2 orbital is overlapped with a hydrogen s to form a sigma bond between the carbon and a hydrogen, and the same is true for this one, and this one. Now this p orbital is overlapped with this p orbital, and one way that we can represent this is we can just kind of say, oh, look, they're overlapped. Or we could try to redraw it so that here's our sp2 orbitals, and then we can make this big giant p orbitals. So now we can see that they really do overlap. But this is a little bit harder to see overall. You can think about it this way, but I tend to draw it this way, and then I just kind of fudge it a little bit that there's overlap. It's just a representation. Okay, so then what we get from this is a carbon double bonded to another carbon. Going back behind is a hydrogen, in front is a hydrogen, going back behind is a hydrogen, and in front is a hydrogen. And this is the same as writing it like this, where all of the atoms are in the plane of the screen. It's not a rule, but in general, I think it's really helpful to draw as much as possible in the plane of the screen, in the plane of the paper. But I wanted to draw it this way because we started out showing our sp2 orbitals perpendicular to the plane of the screen so that we could include our p orbitals. So if we're looking at it like this, we need to remember that the sigma bond between the two carbons has the electron density along here, and the pi bond between the two carbons has electron density up above and down below. If we're looking at it from this perspective, that means that our sp2 orbitals are all in the plane, and then our p orbitals would be in front of the screen and behind the screen. Now, just to clarify the bonding, this bond is created by the overlap of a carbon sp2 with a hydrogen s. So is this one, and this one, and this one. Here we have a sigma bond that's created by the overlap of a carbon sp2 with another carbon sp2. And I'm running out of room. And here we have a pi bond that's created by the overlap of a carbon p with another carbon p orbital. Again, keep in mind, for our sigma bonds, the electron density is along the axis that joins the atoms. And if we were to look at it in cross-section, we're going to have a circle. But for a pi bond, our electron density is above and below the axis that joins the atoms. And if we look at it in cross-section, it is going to look more like this, with a node that goes along here. So to summarize then, whenever you see a carbon that is connected to three groups, then it's possible that that carbon is sp2 hybridized, and there will be a trigonal planar arrangement. Next, let's consider the possibility if carbon is attached to two groups. So this would be the case in acetylene, also known as ethyne. So each carbon is connected to two groups, and remember our electron configuration for carbon is 1s2, 2s2, 2px1, 2py1, and we focus on our valence electrons so that we have our 2s orbital with 2 electrons, our 2p orbitals with 2 electrons as well. Once again, we can imagine going to an excited state so that we have 1 electron in the 2s orbital and 3 electrons, 1 each in the 2p orbitals. And now we can think about a hybridization or a blending, but this time we're going to combine 1 s orbital and only 1 of the p orbitals. So this gives us 2 new orbitals that are sp hybridized. Sp because it's 1s and 1p orbital that are combined. And then that leaves us with 2 unchanged p orbitals. Fill in our electrons, and we have 2 electrons in the sp and 2 electrons in the p orbitals. With our half-filled sp orbitals, we can form 2 sigma bonds, and with our half-filled p orbitals, we can form 2 pi bonds. Continuing with valence bond theory and hybridization, focusing on sp hybridized orbitals, we need to keep in mind that these orbitals have the same energy as each other, and that energy falls between the s and the p orbitals. In terms of shape and geometry, the shape is going to look something like this with the nub, and we ignore that nub so that it's something like this. The geometry, if we have 1 sp orbital and another sp orbital, they are going to be in exact opposite direction. So we have an angle of 180 degrees. So a carbon with sp2 hybridization, we're going to have 1 sp orbital and a second sp orbital. And then we are going to have an unchanged p orbital. And we're going to have another unchanged p orbital. So this one would be going back behind the screen and in front of the screen. And if you keep in mind the electron configuration, we would have 1 electron in this sp orbital, 1 electron in this sp orbital, 1 electron in this p orbital, and 1 electron in this p orbital. Now, how do we put this together to explain the bonding in ethine or acetylene? So let's say this is our first carbon with an sp orbital and another sp orbital. And here is our second carbon with an sp orbital and another sp orbital. This one is half filled, and these are also half filled. In addition to the sp orbitals, we have a p orbital and a p orbital over here, and we have a p orbital going behind and in front, a p orbital going behind and in front, with 1 electron in each of these and 1 electron in each of these. And then finally, we have a hydrogen S and another hydrogen S. So this sp orbital is overlapped with this sp orbital, forming a sigma bond between the 2 carbons. This sp is overlapped with a hydrogen S, forming a sigma bond between the carbon and the hydrogen. Same thing over here. This p orbital is overlapped with this p orbital that's parallel to it, giving a pi bond, which has electron density above and below the axis that joins the atoms. And then these green p orbitals are parallel to each other, and they will also overlap, forming a pi bond. So this gives us this compound where this bond is created by the overlap of a carbon sp with a hydrogen s, and that is a sigma bond. Same thing over here. Here we have a sigma bond that is created by the overlap of a carbon sp with a carbon sp. We have a pi bond created by the overlap of a carbon p orbital with a carbon p orbital. and a second pi bond formed by the overlap of a carbon p orbital with another carbon p orbital. If we were to focus on the carbon-carbon bond, let's say that we are looking at it from the side. Here is our back carbon, and then we're putting our front carbon right in front of it. We're going to have the electron density for the sigma bond is going to go like this. So that is the sigma. And then let's come back to the colors that I used over here. For our red p orbitals, we are going to have a pi bond, which gives us electron density above and below. And then our green p orbitals will give us a pi bond, where we have electron density to the left and the right. So this is the cross section of our sigma bond. This is the cross section of one of our pi bonds, and this is the cross section of our other pi bond. So whenever we have a carbon that's connected to two groups, then we're talking about sp hybridization. Now that we've talked about sp3, sp2, and sp hybridization, let's take a look at this structure and figure out what we can about the hybridization, the shape, and the bonds. So what we need to keep in mind is that if carbon is connected to 4 groups, it'll be sp3 hybridized. If it's connected to 3 groups, sp2, 2 groups, sp. So in this case, Z is connected to 1 group, 2 groups, so it must be sp hybridized. Looking at Y, this is also connected to 2 groups, so this is also sp hybridized. Looking at X, this carbon is connected to 1, 2, 3, 4 groups, so it must be sp3 hybridized. W is also connected to 4 groups, so W is also sp3 hybridized. V, this carbon is connected to 1, 2, 3 groups, so 3 groups must be sp2 hybridized. The atom labeled U is connected to 1, 2, 3 groups, so that must be sp2 hybridized. And finally, T is connected to 1, 2, 3, 4 groups, so this must be sp3 hybridized. Again, to determine the hybridization, just look at how many groups that atom is connected to. Next, as we think about shape, well, to determine the shape, we just need to think about the hybridization. Because this is sp hybridized, then these groups must be linear. Looking at Y, we know that this is sp hybridized, so again, these groups must be linear. With X, we have 4 groups. We said this is sp3 hybridized. sp3 hybridization gives us a tetrahedral arrangement. With W, we have 4 groups. Again, sp3 hybridized. So this is, again, tetrahedral. With V, we're connected to 3 groups. We said it is sp2 hybridized. So this one will be trigonal planar. Carbon U is also connected to 3 groups. It's also sp2 hybridized, so it will also be trigonal planar. And finally, T, this carbon's connected to 4 groups. We said it's sp3 hybridized, so it must be tetrahedral. So looking at the groups, we figure out the hybridization. Based on the hybridization, we figure out the shape. Next, we want to think about the bonds. So if we look at the bond labeled A, that's between this hydrogen and this carbon, we know that this carbon is sp hybridized. And so that overlap then must be a carbon sp overlapped with a hydrogen S. And that's what makes this sigma bond. Next up, we have B. B is a triple bond, so we have to explain the bonding for all 3 of them. So those carbons are sp hybridized. So we're going to have a sigma bond due to a carbon sp overlapped with another carbon sp. We're going to have a pi bond created by the overlap of a carbon p with a carbon p, and another pi bond, carbon p overlapped with carbon p. Bond C is between an sp hybridized carbon and an sp3 hybridized carbon. So we have a carbon sp overlapped with a carbon sp3. For D, we're looking at an sp3 and an sp3. So this bond is created by the overlap of a carbon sp3 hybridized orbital with another carbon sp3 hybridized orbital. For E, this is sp3 hybridized, this is sp2 hybridized, and we're talking about a single bond, so this is a sigma bond. So E is a carbon sp3 hybridized orbital overlapped with a carbon sp2 hybridized orbital. Next up, we're looking at F. This is a double bond, and we have to explain both. So these carbons are sp2 hybridized. With a double bond, we have one sigma bond and one pi bond. So our sigma bond is created by the overlap of a carbon sp2 hybridized orbital with another carbon sp2 hybridized orbital. And our pi bond is created by the overlap of a carbon p with another carbon p orbital. If we look at G, this carbon's sp2 hybridized, this carbon's sp3 hybridized. So G would be created by the overlap of a carbon sp2 hybridized orbital with a carbon sp3 hybridized orbital. H, we're looking at a carbon that's sp3 hybridized overlapped with a hydrogen. So this would give us a carbon sp3 overlapped with a hydrogen S. And finally, I, we have our hydrogen bonded to our carbon that is sp2 hybridized. So this bond must be due to a carbon sp2 hybridized overlapped with a hydrogen S. So by focusing on how many groups are connected, then we can determine the hybridization, we can determine the shape, and then by looking at the hybridization of the atoms at the end of the bond, we can also figure out which orbitals overlap to create a particular bond. Now we've been focusing on carbons, which could be sp3 hybridized, sp2 hybridized, or sp hybridized. What about other elements? Well, the same thing can apply. If we think about the electron configuration of oxygen in an atom, this is 1s2, 2s2, 2p4. I didn't leave myself enough room, so I'm not going to break it down further. And the electron configuration of oxygen in a molecule is not necessarily the same. So let's fill in our electron configuration, just focusing on the valence electrons. So we have 2 electrons in the 2s orbital, and then in the 2p orbital, we have 1, 2, 3, 4 electrons. We could imagine that these 4 orbitals could be hybridized to give 4 new orbitals, and we would have 1, 2, 3, 4 sp3 hybridized orbitals. Filling in our electrons, we have 6 valence electrons, so 1, 2, 3, 4, 5, and 6. So notice we have 2 filled orbitals. This would be a lone pair, and this would be another lone pair. And then we have 2 half-filled orbitals, which means that oxygen can form 2 bonds. So if we were looking at a molecule of water, for example, this oxygen is connected to 1, 2, 3, 4 groups. So the oxygen is sp3 hybridized. This lone pair and this lone pair would be these electrons. And then this bond would be created by the overlap of an oxygen sp3 with a hydrogen S. And the same thing over here. Let's look at another example sticking with oxygen. And we have 2 electrons in our 2s and 4 electrons in our 2p. What if we blended the s orbital and 2 of the p orbitals? The combination of these 3 orbitals gives us 3 new orbitals, 3 hybridized orbitals, and these are sp2 hybridized, leaving us with 1 p orbital unchanged. Fill in our electrons, and we have 1, 2, 3, 4, 5, and 6. So here we have our lone pairs. Here we have a half-filled orbital that can form a sigma bond, and here we have a half-filled p orbital that can form a pi bond. So if we are looking at something like formaldehyde, this carbon is connected to 3 groups. So we would say it is sp2 hybridized. This bond and this bond are created by the overlap of a carbon sp2 with a hydrogen. Here we have 2 bonds, and so the sigma bond would be created by the overlap of a carbon sp2 and an oxygen sp2, and then a pi bond would be created by the overlap of a carbon p orbital with an oxygen p orbital. These lone pairs would be residing in sp2 orbitals. Although we spent the most time looking at carbon atoms talking about sp3, sp2, or sp hybridization, the same thing can be applied to oxygen, to nitrogen, to the halogens. Many other elements will also follow the same type of hybridization.